All right, good morning, everybody. Thanks for joining us for Blackhat relatively early hour and for making the long journey down unmarked hallways and having the dedication to actually find the room. So my name is Brad Hill. I'm a principal consultant with ISEC Partners.
My name is Scott Stender. I'm a partner at ISEC Partners.
My name is Rachel Engel. I'm a security analyst at ISEC Partners.
And we all work in their application security consulting practice, and the three of us are based out of Seattle. So we're here this morning to talk about attacking Kerberos deployments. Kerberos is one of the oldest security protocols that's still in wide use. And as for any protocol that is of that age and that level of complexity in deployment, there are lots of caveats, warnings, configurations, and notes in RFCs and policy statements and operating systems for configuring it. And these tend to be kind of cryptic and hard to understand, so much so that just about every deployment we've ever looked at has at least some set of services that are not taking advantage of the full set of security properties available of Kerberos or are configured in ways that are just wildly insecure, unfortunately. So we're here to, we read the RFCs so you don't have to, and read the policies so you don't have to, and we're going to explain to you what do those warnings actually mean in terms of practical attacks, and what can you do as developers and as administrators of these systems to make your lives more secure when you're using Kerberos. So we're going to start today on our agenda with a quick overview of the protocol. So those of you who don't live in the jargon every day like us will have some idea what we're talking about when it starts to fly. We're going to talk about the initial authentication steps of Kerberos and some attacks against e-type negotiation. We're going to go into public key Kerberos as it supports smart card login and look at an attack there that is active against just about every single Active Directory system deployed in the field today that allows user-to-user elevation of privilege. And owning one box, eventually elevating to owning an entire enterprise. And then we're going to look at the establishment of sessions to applications with Kerberos and how those might be hijacked and what are some of the precautions that we can take to protect against replays and ensure that we're talking to the services we really think we are. So, a very brief introduction to Kerberos. Kerberos is a trusted third-party symmetric key exchange protocol based on the Needham-Schrader protocol from 1978 and then formalized over several versions into the current form of Kerberos 5 today. But the basics are still the same. You have a trusted third party, the KDC, which is the Key Distribution Center, and it has a shared secret with everyone else that participates in Kerberos. And that's a set of principles for which the KDC has shared keys is called the realm. So here we see a KDC has a shared secret with a client and with a file server. And our scenario is the client wants to talk to and establish a secure connection and authenticate itself to the file server. So the client begins that by talking to the KDC. It uses its long-term shared secret, usually a password, to make an authentication service request to the KDC. And the KDC replies, again verifying with that same long-term shared secret, and it issues the client a new short-term key. This is key associated with a ticket granting ticket. So we don't want to continue to expose that long-term key on the network many times, so we create a new short-term key, and the client uses that short-term key to make a request for service to the file server. KDC replies using the short-term key, and it creates a session key to be shared between the client and the file server. It gives one copy in a form that the client can read and gives another copy encrypted so that only the server can read it. The client can then form a service request to the file server, can authenticate it with that short-term key, and then it sends the server its copy of the key encrypted so that only the server can read it. Server unwraps the key, verifies the signature on the message that came from the same key, and then it can provide services to the client, optionally verified and signed and sealed, whatever, with that short-term session key. So these are the basics. And why you should care is because this stuff is everywhere. If you've ever logged on to a Windows Active Directory network, if you participated in a large-scale Unix Linux deployment on a university or any other type system where you have a large centrally administered intranet network, Kerberos is the underlying protocol for all of that. And it's not just there. Because it is so widely deployed, it's being adopted continually in new places. One of our other consultants, Andrew Becker, is going to talk about Kerberos and Hadoop later on in the conference. It's being used for web services. It's being used for InfoCard and federated services as a binding to allow intranet identities to be moved out to the web. And so it really is the sort of hidden glue that holds all of our security together in an enterprise environment and extending out to the web. We're going to start at the beginning with our advice and look at the initial authentication and how that is set up, and I'm going to hand it over to Scott Stender to do that portion.
Well, thank you, Brad. So one of the main drivers for Kerberos v5 was that Kerberos v4 did not have cryptographic agility. All symmetric keys, all encryption that happened in the Kerberos v4 protocol used the DES encryption algorithm, which we all know, if we've been paying attention to security in the last few years, it's not sufficient to protect traffic today. So in Kerberos v5, you introduce the ability to negotiate which cryptographic primitives, encryption algorithms, hashing algorithms, and whatnot to use for protecting different Kerberos message exchanges. Examples of what are called encryption types. I'll call them E-types during this talk for short. Examples of E-types include AES 256 and ciphertext sealing mode with an HMAC that uses SHA-1 as the hashing algorithm, and so on. So you have AES 128, RC4 HMAC, which is actually something that came from Windows. It was introduced with Windows 2000. It's not a standard, but you can find guidance on how it's implemented. And that uses a 128-bit RC4 key. You have DES CBC MD5 and RC4 HMAC, similar to RC4 HMAC 128, except for it's truncated to a 56-bit key. So how are E-types negotiated? Now, Brad just went through the whole protocol. I'm going to focus on the AS-REC exchange. Now, there is no specific standard for negotiating E-types. At best, you could call them ad hoc standards, but clients and servers are free to do more than having a standard negotiation stage. But what you'll see most often is, if you're looking at network trace, is a couple of attempts to authenticate where negotiation happens through those attempts and error messages that are returned. So the first stage, you'll have the client send what I'll call an anonymous AS-REC. The AS-REC is authenticated using a structure called the ENC timestamp. That's just a timestamp that's AS1 encoded, a little bit more data that's encrypted using a key derived from the user's password. So at first, they do an anonymous AS-REC, which is, ENC timestamp is null, and then it has the list of E-types that the client supports. Hello, I support AES 256 and DES CBC MD5. The server responds with an error pre-auth required. I'm not going to just give you message, data that's encrypted with the user's key. If you're just anybody on the network, I want you to prove to me first who you are, then I'll happily send you back a little bit of information. In that message, you have a list of E-types. So it says error pre-auth required. By the way, of the messages, all of the E-types you sent me, I support these two, AES 256 and DES CBC. So the server responds with the union of what it supports and the set of what the client supports. The client chooses the best of them, the strongest of them. In this case, without any kind of interaction, it'll choose AES 256. And it'll use that to, use the standard derivation algorithm for going from password to key. It'll use that to encrypt the timestamp, send that up to the server, and it'll specify, hey, this is a big blob, 6BA4 ... and it's using AES 256. And then it also includes a list of E-types to be used for negotiating the TGS key, which is the next stage. The server responds with a AS-REP, which includes the key that is to be used for a TGS request that follow, the authenticator for that. So attacking E-type negotiation. Now, it's not exactly apparent if you read the specifications, the RFCs and whatnot, and it's not really apparent if you look at the network traffic. And also, if you've had experience with other similar protocols that have to negotiate cryptographic primitives, you might be surprised to find that that list of E-types, both from the server and the client, is unprotected by any kind of integrity mechanism. Right now, it's all pre-auth, and so the attacker has the ability to drop good E-types and leave bad ones behind. So what does this allow us to do? It allows the attacker, a full man-in-the-middle attacker, to drop the good E-types when the client is sending that initial anonymous AS-REC. The Kerberos server will then respond back with that error pre-auth required message that includes only what the client supports and that it supports as well. So if you just say, hello, I support only DES, server will look up and say, do I support DES? Yeah, great. Okay, here, let's go with the DES. You can also downgrade the authenticated AS-REC, in which case you're going to influence the next stage. Or you can intercept the server response back to the client, that error pre-auth required message, and you can downgrade and lie to the client about what the server supports. In both cases, the end result is the same. The ENC timestamp, that authenticator, that which is derived directly from the user's password, is going to be using a cryptographic method that's not exactly the most secure thing in the world. Now the benefits of that. So if I am able to downgrade to DES, DES is a rather older and somewhat simpler E-type than the latest and greatest. There is no keyed authenticator within the encrypted timestamp. Furthermore, the only key that's derived is the encryption key that is used to protect that encrypted timestamp. So what you have is a one-time, take this string, make it into a password, or into a key, and that key remains the same key that's always used to encrypt ASREC ENC timestamps from now until the user changes their password at the same time. In effect, if you get that key, you're able to have a password equivalent for Kerberos and use that for several months until they change your password once again. So the end-to-end attack scenario is, get active man in the middle on a network that uses Kerberos, downgrade that initial ASREC or the response to error pre-auth required, go down to DES. You're going to see the client emit that encrypted timestamp, and then you can hand it off to our friends who are also at this conference, Pico Computing. Here you see a card that is an FPGA cluster. Back at Blackhat Federal, they demonstrated breaking a DES key in as little as 3 days using older hardware. Presumably with more hardware and this newer hardware, we could break that down into shorter number of days or even hours. We can go ask them if we need details on that. So you break the key, now you have that long-term key, and then you can just go back to the network and use that to authenticate the user and get access to any system that they have access to via Kerberos. Alright, so we all know DES is bad. How do we, is that the only thing that can go wrong? The other benefit of downgrade is that, again, the latest and greatest E-types are a bit more sophisticated in trying to protect against password grinding attacks. And by that I mean we take a big dictionary of words, we do the derivation of keys, we encrypt a timestamp and see if the encrypted timestamp can be decrypted using something that would be out of a dictionary. And we can spend a whole lot of time verifying what, trying active keys, seeing what's going on, seeing if we can guess the user's password. Frank O'Dwyer several years ago, maybe 2002, 2005, I think he had an update to his paper, demonstrated that you can have efficient password grinding attacks against a strong E-type that's used widely in Windows, RC4 128 HMAC. Even if you do get rid of DES and you use only E-types that cannot be broken via exhaustive exploration of the key space, you can downgrade to something that allows for efficient password grinding attacks. So for that reason we suggest staying with the latest and greatest because they do try to slow that computation down using PBK-DF2, which is a standard for repeatedly hashing the user's password and the output from the previous hash to make the computational difficulty of deriving a key much greater. You can specify, you can configure the number of iterations. The standard specifies that you should not be able to go below a minimum iteration count. The default is 4096, by the way. But the interesting thing about downgrading is not only can you say go back to RC4 HMAC, you can take advantage of any bad client implementation in that you can specify in that error pre-auth required optional parameters for the key derivation. You can specify the salt that is to be used, which is typically the user's full name. It's the realm and the user's name. Or you can specify the number of iteration counts. And so if you have you can use that wiggle room to perhaps make a more efficient attack. So does this affect me? We talked about DES. We all know that DES is terrible. Windows Server 2008 and Windows Vista, so the latest versions of Windows from just a few years ago, all support DES out of the box. And so the KDCs are willing to accept DES encrypted at timestamps, and Windows Vista clients are willing to emit them. In addition, rather recent open source distributions of Kerberos, MIT, Heimdall, and similar ones that are configured and used similarly, Solaris for example, they also all support DES. Windows 7 emits but does not accept RC4 export grade RC4. You can